Finishing getting set up and then we'll be ready to start. So before we do, I'd just like to thank you all for coming tonight for the lecture Graphene Unexpected Science in a Pencil Lead, presented by Dr. Aravind. Now, this is part of the European City of Science event, which is currently being held throughout the city of Manchester. Dr. Aravind works for the University of Manchester in the Nanomaterials department. He does work on research into graphene and other 2D materials. His lecture tonight will be telling us about the wonderful new material graphene. What is it? How is it made? What benefit can it be to us? Tonight's lecture and the other lectures that are being presented by the young professionals community will eventually be on their YouTube channel once they get that set up and running. But in the meantime, for more information about the young professionals community, you can visit the Facebook group or Twitter account. We've got the IET community account as well. There's no scheduled fire alarms tonight, so if you hear any, that's a real one, so just quietly move to the closest exit. Just a few quick thank yous before we start. I'd like to thank Dr. Aravind for giving up his time to come here tonight to talk to us, and Leona for setting up the venue and all the catering. I think that's everything, so I won't take up any more of your time. Welcome, Dr. Aravind.
Thank you. Can everybody hear me there? You there? Excellent. So welcome everybody. Thank you for coming to hear my lecture about graphene. How many of you have heard of graphene before? Right, I can skip through the first half of my talk. No, I won't, no, because there's a lot of things you probably don't quite know or don't know correctly maybe, so we'll go through it. So what I'm going to do basically is I'll talk a little bit about what's graphene, what is the structure of graphene, how to make graphene, what its properties are, and then I'll tell you about what it's used for, and then I'll go on to what we call other two-dimensional materials like graphene, tell you a little bit about what we're doing today, and then about also the Graphene Institute at the university. So that's the rough outline of my talk today. So if there is one thing that I want you all to take away from this lecture, is an understanding of what a two-dimensional material is. So graphene is a two-dimensional material. It's the world's first two-dimensional material, or the first material in two dimensions which we have produced. It's also the basis for a number of other materials which they fall under the broad category of low-dimensional materials. So typically, if you think about materials that we use, they're all three-dimensional. There's some kind of sound anyway, it doesn't matter. They're all three-dimensional, which means they have a length, a width, and a height. So if you take carbon, for example, if you remember your high school chemistry or physics, you'll remember that carbon occurs as allotropes, different forms of carbon. You've got diamond, graphite, soot. They're all materials in three dimensions, so they have a length, a width, and a height. However, we nowadays have access to what are called low-dimensional carbon materials. And what do I mean by that? So if you look at a sheet of graphene, it's basically a single sheet of carbon atoms. So you could say, okay, it's one atom thick, it's like a planar structure, so it's two-dimensional. It's not quite that simple, because if you think about it, even a single atom has some thickness, so technically it's not two-dimensional for that reason. However, there are two reasons why graphene is in fact a two-dimensional material. If you look at a sheet of graphene, now you have to do a little role playing here. You have to imagine yourself to be an electron which lives in the sheet of graphene. If you are an electron living in that flat sheet of graphene, you can move back and forth and left and right, but you can't move out of the plane of the atom. So you can't jump up and down, you can't leave in the third direction. For that reason, the electron lives in a two-dimensional world. And many of the properties of graphene, particularly its electronic, optical, and mechanical properties, are not decided by what you and I can see, but what the electron can see. So the electron lives in a two-dimensional world, and for that reason, graphene is two-dimensional. The other explanation for why graphene is two-dimensional, if you look at the sheet of graphene atoms, if you add atoms to the left and to the right, or to the front and back, you get a bigger sheet, but it's still graphene. So you can add atoms in two directions, and you're still left with graphene. If you add atoms above and below and make the crystal grow in that direction, it's no longer graphene. So there are two reasons why. One is the physical explanation, that we can extend the crystal in two directions but not in the third. And the second is the electron sees a two-dimensional world. For those reasons, graphene is a two-dimensional material. You can make similar arguments on why other low-dimensional carbon materials are, let's say, 0 or one-dimensional. So if you take what is known as a fullerene, that molecule over there, which is basically, if you cut the graphene sheet along this shape, you can roll it up and get a sphere. That's known as a fullerene. The atom, the electron living in a fullerene can rattle around on that cage, on the surface of the cage, but net displacement is 0. It goes round and round, but it doesn't actually go anywhere. So it's a zero-dimensional material. If you roll this sheet up into a tube, you get what we call a carbon nanotube. The carbon nanotube is one-dimensional because an electron living in this tube, the net displacement is only along this direction. It can go back and forth, but that's only in the one direction. If you take the graphene sheet and you stack it up, you get the familiar graphite. So graphite is basically many layers of single atomic layers of carbon, like a deck of cards stacked up on top of each other. Another way of looking at it is if you take graphite and you keep cutting the deck, ultimately you get a single card, and that single sheet of graphite is graphene. So, as I told you, graphene is a single sheet of graphite, so it's the fundamental building block of graphite. For that reason, graphene has been studied as a theoretical material for a very long time, because graphite is technologically a very important material. It's not just for pencils, but it's been used in nuclear reactors, for example. So it is a very, very technologically important material. And to understand the properties of graphite, you first need to understand the properties of graphene. However, no one until recently had been able to actually make a single sheet of carbon atoms and measure its properties. So even though we have a mathematical model and we could predict some of the properties of a single carbon atom sheet, no one had actually succeeded in making it. And one of the reasons for this, a lot of people believed, was because they couldn't make it, because there is a theory which states that if you have a purely two-dimensional sheet of atoms, it's thermodynamically unstable and it will sort of destroy itself. And, graphene does exist. So it's a funny situation where it's not that the theory is wrong, but the graphene has found a way to cheat the theory. So we'll come to that in a second. But the first graphene was made or isolated. I'll say isolated because it was removed from the graphite where it is contained. So you start with graphite and you reduce it down to a single layer of graphene. This was in 2003. The paper was published in 2004 by Geim and Novoselov from Manchester Uni. And for this, and then they went on to study the properties of graphene. They were responsible for the vast majority of the understanding of graphene that we have today. And for that, in 2010, they were awarded the Nobel Prize. Since then, they've gone on to win a number of other awards. They've been knighted and so on and so forth. And this paper in 2004 by Geim and Novoselov was regarded in a sense as the graphene start of the graphene rush, or the graphene gold rush, because literally nowadays every major university in the world has some kind of graphene research going on. Most companies in the world have either an active graphene activity or have dabbled in it at some point. So it's really become a worldwide research topic, not just in academia, but in industry as well. So what you see here is a piece of silicon wafer with a hole cut in the middle and a sheet of graphene on top of the hole. So clearly this piece of graphene is perfectly happy suspended in free air on top of the hole. This shouldn't happen. However, the theory that predicts that this shouldn't happen assumes that the sheet of graphene is perfectly rigid and flat, when in fact it isn't. So the sheet of graphene here that you see over the hole actually contains a lot of ripples and waves in it. So this, in a sense, simplistically, serves to stabilize the sheet of graphene, absorb any excess energy. So that's a schematic of what the rippled graphene sheet looks like. And we've seen this in electron microscopes, so this is not just a theory. We know this is what actually happens. The contrast isn't terribly great. I don't know if there's a way to switch the lights off just there. Do you have any idea if that's possible? Yeah, that would be really helpful. Just the podium lights, if you could switch them off, please. Sorry about that. Oh, that's fine. That's fine. As long as they can see the contrast on the screen improves a little bit. So if you look at that, this is a transmission electron microscope image of a sheet of graphene. If you see, there are white dots arranged in a hexagonal pattern. So it kind of looks like chicken wire. So each white dot is a single atom of carbon. We have now the capability to see individual atoms of carbon. And like any other material, it's not perfect. Ever so often, you will see locations where there is a carbon atom missing, a defect in the lattice, which occurs in any lattice in any material. If you are curious, there are, for Android and Apple devices, apps that we have, an app that we have made, which is basically a virtual electron microscope, where that image I showed you before and many, many other images like that. It's sort of like Google Earth for graphene, if you wish. You have a sheet of graphene with lots of different features. You navigate around and you can see for yourself. This is the sort of the interface. There's a box that tells you what you're seeing. There are options, different regions of the graphene that you can select. That tells you the size of the feature you're looking at, the magnification you're looking at, and so on. So feel free to have a play. Okay, right. Next I'll talk a little bit about how graphene is made. The first way that graphene was made by Andrei and Kostya was a very simple but very elegant method. As I told you before, they started with graphite and they got a sheet of graphene out of that. How did that happen? How did they do that? Well, they took a sticky tape, which in popular culture has been referred to as the sellotape or the scotch tape, depending on which side of the Atlantic you are. But in fact, the sellotape they used was about 800 pounds a roll, so it's not quite sellotape. But you use the sticky tape and you peel a few layers of carbon away from a sheet of graphite. And then you take those layers and you stick it on another piece of sellotape and you peel it again. So every time you do that, it's like you're cutting the deck of cards. Sorry. You keep cutting the deck, so you keep peeling with the tape until you end up with a single or few layers of graphene. And you transfer those layers down onto a piece of silicon. And I'll come to that in a second, why we use silicon wafer. And then you put that under an optical microscope. Any laboratory optical microscope that you might find in a school will do. You don't really need a very special microscope or anything like that. And you will see something which looks like this. So what you're seeing there, basically, the yellow regions are relatively thick bits of graphite. The blue regions, it's getting thinner and thinner. And somewhere in this mess, if you zoom in even further, you'll see a very, very light contrast, a very light, slightly darker shade of purple than the color of the substrate. This slightly dark purple patch here, that's a single layer of graphene. Adjacent to that, you'll have slightly darker patches, which are 2 layers, 3 layers, and so on. The best analogy I can think of is Where's Wally? So basically, every time one of my PhD students goes into the lab, they see something like that. The job then is to find the graphene hidden amongst all the other bits of graphite. It's got a lot easier these days. The original piece of graphene was about that big, which was a few microns, which is about 10 to 50 times as smaller than the width of your hair. So quite tricky to find. But nowadays we can make graphene particles which are a few hundred microns, so half a millimeter in size. It becomes a lot easier to find it. As part of our outreach activities, in addition to giving lectures such as this, we also run outreach events at science festivals. For example, Manchester Science Festival, which is coming up later this year. We have a stand where we have an optical microscope, some bits of sellotape, graphite. You can go along, have a play, make yourself some graphene, stick it under the microscope, like that young girl has done, and find the graphene for yourself and see what it looks like. So if you would like, keep your ears and eyes open. When Manchester Science Festival or anything else like that. In fact, in July, we have the Euroscience Open Forum. Manchester is the city of science. The Museum of Science and Industry is going to be running a graphene exhibition, and this will be a part of that. So spread the word, go have a play, make your own graphene and see what it looks like. But more importantly, there will be people like me, both PhD students and scientists at the stand that you can talk to. If there's something that I don't explain properly today or you haven't had a chance to ask me, you can go and ask them. So, yeah, that's coming up. However, the method I just described with the sellotape is not what you would call scalable. It's scalable to the sense of how many PhD students I have, but it's not scalable in the sense you can't implement it on a factory floor. So if you want to actually make something useful with graphene, you need a way of making the material in large scale. There are a couple of established ways of doing that. One is what we call chemical vapor deposition. In chemical vapor deposition, basically you take a gas which contains carbon, because graphene is made of carbon. So this gas is typically methane. And you pass the gas over a hot sheet of metal. The methane will decompose in the high temperature. The carbon atoms will assemble themselves into a sheet of graphene on the surface of the metal. Okay? Because this is a mature audience, I can tell you that methane is the constituent of cow flatulence. So basically we're lighting farts. So once you have the graphene sheet on the piece of metal, you can then transfer it onto other substrates like a silicon wafer, for example, and then you can actually make something useful with it like electronic circuits. Another way of making graphene, this method is scalable because you can implement it on, for example, a roll-to-roll process. So you have rolls of copper foil, they go through a furnace, they get coated with graphene, and then they go through another lamination furnace and an etching furnace. On the other side, you get, let's say, a sheet of glass or a sheet of plastic or something like that coated with graphene. This could be used, for example, let's say in display applications and things like that. I'll come to that later, but you can see there is a sheet of plastic about 30 inches diagonal, the size of a decent telly, covered in graphene. Yeah? The other way of making graphene is, instead of starting from a carbon gas, you start from graphite as you did before for the sellotape method. But instead of using a sellotape, you use some form of high energy. So you can either blast it with ultrasonic energy or some other kind of chemical. You add some acids or something like that, and you break the graphite apart, and you release the individual pieces of graphene into some kind of a solvent. It could be water, it could be some other solvents, organic solvents. And what you end up with is a bottle of graphene dispersion. It's kind of it's a colloid, it's like milk, except it's black. So you have a bottle of graphene ink where little particles of graphene are floating around in a solvent. This can then be used for a variety of different applications. Now, this chart here talks about the three methods of production I've told you so far, and also some other methods that I haven't gone into, and plots it on the x-axis as a function of price. How expensive is it to make a unit quantity of graphene? And on the y-axis, the quality of the material. The sellotape graphene that we started off with is still the best quality of graphene we can make, which means the individual pieces of graphene, even though they're very small, The atomic quality, the number of defects is the lowest, the crystal structure is the most perfect, there are no impurities. It's still the cleanest and highest crystal quality graphene that we can make. However, because you're making it one little piece at a time, it's jolly expensive. So it's very good for prototyping, for studying the basic properties of graphene, but it's not much good for any real application. On the other extreme, you have the liquid phase exfoliation, which I just described, where you disperse the graphite into a solvent. Because you're using a lot of high energy to break the graphite up, you introduce a lot of defects. The individual particles are quite small, but it's a way of mass production in the sense you can make liters or tons of graphene. Therefore, even though the quality is not the best, the price is the cheapest. The other method, the chemical vapor deposition, gives you better quality at a higher price. So, depending on what application you want to use it for and what price you're willing to pay, you have to decide which is the best way for making graphene. Even this, let's say if you take this method, it's not a fixed point in the chart. There are ways of spending more money and making slightly better quality, or spending less money and making slightly worse quality. So basically there's a way of making graphene that fits pretty much everywhere on this chart. But it's not just the price or the quality that determines which graphene you use, it's also the application. If you want to mix the graphene in with a plastic to make an object, you're pretty much only able to use the liquid exfoliated graphene because it's in the right form. You can't use anything else. If you want to coat a surface and make a display, you want a perfect continuous coating of graphene, the chemical vapor deposition is your only option. So very often the technology limits which graphene you select, but in some cases it doesn't, and then the price might be the determining factor. But it's not, so all of these amazing applications of graphene and the great degree of interest in graphene is because graphene is a very unique material in terms of its properties. Graphene has it's a long list of superlative properties. When I say superlative, I do mean superlative because it's the best in a lot of things. So, it's the strongest material that man's ever measured. It's the best conductor of electricity. It's the best conductor of heat. It's completely impermeable. Nothing can get across a sheet of graphene. It's very elastic, which means you can take a sheet of graphene and stretch it. It's bendable. You can fold it. You can wrinkle it. You can crumple it. It's almost like a cloth. It's got a very high surface to volume ratio, which means that basically every atom of graphene is at the surface of the material, twice over, once at the bottom and once at the top. So there are lots of amazing properties of graphene. It's very transparent. It's about 97% transparent, so 97% of the light goes straight through it. So it's got lots and lots of amazing properties. But the thing about this list that is particularly exciting to me is the bit in the last, the 3 dots. It's everything we still haven't figured out. Because this is not a complete list. We're still doing a lot of basic, very, very basic research. And there's still lots of new properties of graphene which we've either not fully studied or fully understood. For example, the electron mobility, how fast an electron can travel through graphene. On a regular basis, somebody keeps coming up with a higher number because they've figured out a better way to make the device. And then there are also brand new properties. Every once in a while, graphene comes along and surprises us with something that we hadn't known before. So this is a growing list. This is not a complete list. So it's not like we've understood graphene completely and we can go off and do applications. We're still in the process of understanding the material. I just put this slide up mainly it's sort of a little serendipity anecdote. I told you before when I was telling you about the sellotape method that at the end you put it down on a piece of silicon. One reason why you use silicon is because it's very popular in the electronics industry. All electronic chips are made with silicon wafers, and therefore silicon wafers are cheap. and it's a very clean, flat, cheap substrate. Normally a silicon wafer has on its surface a layer of oxide, silicon oxide, which has a particular thickness depending on what application you use it for. Now, if you take graphene and you put the sheet of graphene on a silicon wafer which is having 300 nanometers of silicon oxide on the surface, and you look at it just in white light, you can kind of see the graphene. However, if you look at it under a particular like green color light, you can see the graphene very, very clearly. However, if you look at it under some other color of light, it completely disappears. Similarly, if you take the graphene and put it on a silicon wafer with 200 nanometers instead of 300, then you can't see it at all in white light. But there are some light frequencies where you can actually see it. So the serendipity aspect of the discovery of graphene is basically when Andre Geim and Kostya made the first samples of graphene, they just happened to have silicon wafer of that thickness on hand. If on that day they had used that and looked at it under the white light, they would never have seen the graphene, even though it was there. So there is a bit of serendipity involved in this as well. But fortunately, being good scientists, they didn't stop there. They then went on to actually work out the physics, why this happens, and explain very nicely and give a predictive prescription. If you put it on this substrate, you'll see it. If you put it on that, you won't. So, there was very, very nice papers coming out of explaining this phenomenon. The other thing I want to also emphasize here is when I say, for example, graphene is the strongest material in the world, you can't imagine a case where I'm going to have a big sheet of graphene, you pull it at one end and I pull it at the other end. It doesn't work like that. A tiny crystal of graphene, which is atomically perfect, is the strongest material in the world. Okay? So, how do we measure such a tiny crystal of single layer of atoms? It's not easy. What we do is we put, remember I showed you that image of a hole in a wafer covered in graphene. So we make something like that. We take an extremely sharp needle and we try to puncture the hole. It's like bursting a balloon, except that the needle that we use has to be made of diamond, otherwise the needle will break. So we puncture the graphene, and then we measure the force that it takes to puncture the graphene, and then we use a fairly complex mathematical model of that interaction to indirectly extract the strength of graphene. This does not mean that if you make a large sheet of graphene, it's going to be as strong. So the trick is, or the question you have to ask is, how do we take a large number of little tiny pieces of very good, very strong graphene and make it into a large object of some kind that we can actually use, which retains some, if not all, of the strength of graphene. So when I tell you graphene is the strongest material in the world and it's super light, some people immediately imagine planes made of graphene flying around. It doesn't work like that. I'm going to skip that. So I'll now come to some of the potential applications of graphene. So what sort of things are we anticipating graphene will be used in or can be used in? One of the most exciting potential applications of graphene is as a conductive transparent coating for displays. Anytime you have a display, there are multiple coatings of a material which is typically indium tin oxide, which has two properties. It's transparent and it's electrically conductive. This is what allows the screen to work, the light to come out. It's what allows you to touch the screen, interact with it, and so on. Now, unfortunately, the property of a material which is responsible for making it a very good electrical conductor is also the same property which is responsible for absorbing light. So typically, if a material is a good conductor, think of any material, gold, silver, copper, whatever, if it's a good electrical conductor, it is not transparent. Indium tin oxide is the only commercial material which is both conductive and transparent, and graphene is the other one. So graphene has to be developed to the stage where it is cheap enough and reliable enough and scalable enough to replace indium tin oxide. And when we reach that stage, which is almost there, you will start to see displays on phones and tablets with coatings of indium tin oxide, of graphene rather than ITO. However, graphene has a feature which is that it's bendable, it's flexible, and it won't crack or break. Indium tin oxide, on the other hand, if you take a screen coated with ITO and you bend it, it will crack. So in the future, if you imagine that you will have devices which can be bent or folded like electronic paper, you need something which is a good conductor, is transparent, and also flexible. So that's why graphene will really shine. The other major application of graphene is composites. I alluded to this before. You take a plastic, which is typically soft, you add graphene to it. The graphene imparts some of its strength to the plastic and makes the plastic stiffer, firmer. Typically plastics are good because they're light and they are inert. So we like things that are made of plastic rather than metal. They're cheaper, but they're not very strong. So one application of graphene's strength is to strengthen a plastic. However, graphene is also an electrical conductor, and typically plastics aren't. So if you are trying to replace something that is made of metal, you want it to be lighter, but you also want it to be electrically conductive or conduct heat, then you can't replace it with the plastic. But if you take a plastic, you mix it with graphene, it makes the plastic stronger, conduct electricity, conduct heat. So you now have a material which is strong, light, and can potentially replace metals. So that's another example of how graphene could be used. The third very exciting application of graphene is in filtration. So if you take, so in this case, first I'll describe something called graphene oxide, which is a modification, a chemical modification of graphene. If you take this material, graphene oxide, which is also like graphene, it's single sheets but with some chemical groups, and you make a filter paper with it, something like a coffee filter. It has the property that it will let water go through, but it will hold back pretty much everything else. So it has a lot of technological relevance. For example, to separate alcohol and water. And this is very important in biofuels production, for example. So if you want to make sure you get biofuels, in the process you have to separate alcohol and water. If you make a similar filter paper or a coating of graphene rather than graphene oxide, then it's completely impermeable to everything. It doesn't even let helium or even the smallest gas molecules or nothing. It's a perfect barrier. So then you can imagine using it for things like food storage. You don't want any oxygen getting in there, or corrosion protection. Coat a steel object with graphene paint and it doesn't corrode. There's also a lot of excitement and a lot of research going into biomedical applications of graphene. Again, going back to this graphene oxide that I described to you previously, little particles of graphene oxide have the property that they can enter cells. On one hand, this is worrying, but on the other hand, it's been shown that if a little particle of graphene oxide, pure particle of graphene oxide goes into most cells, it's not harmful. And in fact, you can piggyback drugs and things like that. So you can use it as a vehicle or a vector for delivering drugs into cells, which typically don't go into cells. So you can also attach certain molecules to the graphene oxide, which will make sure that it only goes into certain types of cells. So you can actually do things like targeted drug delivery. And there are also other applications where you take a sheet of graphene, and this is quite well known actually, pretty much any cell in the body, if you grow it on a sheet of graphene, it grows really well. So they really like graphene as a substrate to grow on. There's a lot of medical applications in the lab where people have to culture the cells outside the body, and they have to keep the cells alive. Graphene substrates are very, very good for this. Graphene is also very good for various kinds of sensors. I told you before that graphene has a very high surface to volume ratio or surface to weight ratio. So you can make a very light sensor out of graphene, which is very small and yet very sensitive, because every atom of graphene will react to its environment. So if you expose a graphene electrical device to different kinds of gases or different pressures, the electrical conductivity of that device will change because the atoms are responding to the environment. You can measure this. However, these devices are not selective, which means that they might have a similar reaction to many different kinds of gases. So what you have to do is add a functionality to the graphene somehow, which will ensure that only the gas that you want to detect will reach the graphene, and then the graphene will tell you how much of the gas there is. So there's a lot of work into engineering selectivity while the sensitivity is already there. Optoelectronic applications, so applications where you have both light and electrical activity, like for example solar cells, photodetectors. Photodetector is just a fancy way of saying the sensor in the camera. So when light falls on a sheet of graphene, it creates electrons which you can detect. There are, I alluded before, there are other two-dimensional materials. It's not just graphene. So these other materials are actually more exciting for photovoltaic and photodetector applications. I'll tell a little bit more about them in a bit. So this is just a smattering of different kinds of potential applications of graphene. There are other things that I haven't really discussed. For example, energy storage. You can make battery electrodes with graphene, supercapacitors for storing energy. You can make inks out of graphene, which you can print. So you can get conductive circuits, printed circuits on paper, plastic, on cloth. So you can print electrical circuits on your t-shirt, for example. So there are lots of applications of graphene which I have not talked about. This is just to give you a flavor, very broadly speaking. So, as I said before, Andrei and Kostya, whom you see here, won the Nobel Prize in 2010 for the citation was for groundbreaking experiments regarding the two-dimensional material, graphene. It doesn't say for the discovery or the invention of graphene, because we later realized that other people had actually made graphene, but they just didn't realize it. But it was for the fact that they made it, they understood it, they explained it, and they taught the world how to do it. Andrei Geim has the distinction of being the only person in the world to have won both a Nobel Prize and an Ig Nobel Prize. So if you Google flying frog experiment, there are lots of videos on YouTube of the experiment that won him the Ig Nobel Prize a few years before, in 2000. So it's a fun watch. I did mention before that you can chemically modify graphene. So you can make other materials which are also technologically very important. You can take graphene sheet and you can, to every carbon atom, you can attach, say, a hydrogen atom, and you get a material known as graphene. Or you can attach a fluorine atom and you get something known as fluorographene. Fluorographene is the two-dimensional version of Teflon, which is technologically a very important material. So you can get the ultimate thin coating of Teflon if you start with graphene. There are also nowadays other two-dimensional materials. So graphite, as I mentioned before, is layers of carbon atoms. There are lots of materials which are made up of layers of atoms. Clay, for example, is made up of layers of atoms. There are lots of materials which have this layered structure. So once we figured out how to make graphene from graphite, you can use the same sellotape method or the same liquid exfoliation method or the same chemical vapor method to make sheets of other materials also in two dimensions. So there's a lot of research activity into making more and more materials in two dimensions, because the two-dimensional version usually has a lot of different properties to the three-dimensional version. So it's a unique material. It behaves differently. So here are some examples. That's called molybdenum disulfide, tungsten disulfide, boron nitride. Graphene is electrical conductor. These two guys are in semiconductors. One is a direct band gap, the other is an indirect band gap semiconductor. Boron nitride is an insulator. So you have access to a whole library of materials which all have different properties. And where this gets really exciting, so this is the structures of a whole range of two-dimensional materials, and there are hundreds more. But what you can then do is you can start to shuffle them around. So what you can do in the lab, you make a sheet of graphene, make a sheet of molybdenum disulfide, you put that on top. Make a sheet of boron nitride, you put that on top. So you can start to build materials where every layer is a different crystal. And this to me is really, really exciting for one very simple reason. Every time we discover something we think we've been really, really clever, we've realized that nature has gone and done it millions of years ago. But I guarantee you, nowhere in nature are you going to find that structure. So this is a very, very rare example of a completely man-made material, man-made system. So it opens up a lot of possibilities. Why am I putting up the cover of Glamour Magazine from some years ago? Because they did a feature on career of the future, and number 4 on that list was Graphene Engineer. So it's sort of, I'm just using this as an example of saying that it's very much in the popular culture now. It's not just research, it's not just technology or industry. People are starting to talk about it. More and more people are curious and interested in what is graphene, which is kind of why I'm here. This is our National Graphene Institute, which is just across the way over there. It's a facility, it's the largest graphene facility anywhere in the world, dedicated to graphene research. If you walk along the side of the building, you can look into the labs and see what people are up to. That's my research group. Those are the people that do all the work that I take the credit for. So I have to thank them. And yeah, that's it. I'll leave you with that slide, and I'm happy to take any questions. Thank you.
Yeah, absolutely. Is there any questions anyone has? Just like to feel yourself.
When you're trying to layer the different monodimensional materials together, two-dimensional materials together, how do you actually do that? Is it a physical thing, chemical thing?
With lots and lots of sellotape. You literally have to peel one layer off, stick it down, peel another one off, stick it down, and so on. That's the way we do it.
And do they come all together then?
Yeah. We can look in the transmission electron microscope. You can cut a section, look sideways. You can see each individual layer.
Following on from that question, I would have thought the different structures might have different pitches because obviously graphene is a hexagonal thing with a pitch. And if you choose different materials, presumably they'll have different pitches. And there's potentially, I would have thought, it produces strange, perhaps, but new material.
Indeed. And that does sometimes modify the behavior of the material when it is sandwiched between other materials. Yes, it does happen.
They actually use strain lattices in certain types of electronics.
All of that is ongoing research activity, strain engineering. What's the effect of strain? Can we take advantage of it? Or we shouldn't use material X between two layers of material Y because it gets strained in a way we don't want it to be strained. Yeah, that's very much the case.
What's the situation with disposing of, say, plastic that's been treated with graphene? Will it biodegrade, or will you still do it forever?
It's pretty much dominated by the plastic. It depends on the plastic that you're using.
Right.
The graphene itself is graphite, which isn't biodegradable, but it's biocompatible. It came from the ground, it's perfectly happy going back in there. So it's the plastic that would determine its biocompatibility or degradability, not the graphene.
Okay.
Yeah.
You mentioned earlier that the thermodynamics was predicted that graphene couldn't actually exist. How you said it's cheated? How exactly?
It's because it has these waves and
It's the waves.
So thermodynamically, if you have any excess energy,
Yeah.
it would have ripped the sheet apart. But these waves and undulations will absorb that excess energy and keep the sheet from destroying itself. That's the simplistic explanation.
Yeah, my interest is basically in composites and coatings and fluorinated graphene. Can it act as an insulator for high voltage applications?
Yes.
Because my thesis is basically on potential of graphene in advanced materials and transmission systems. So I'm looking into what's the technology readiness level and what's the potential of graphene and its derivatives and for that application.
Dr. Alan Brisden.
Alan Brisden.
He's the guy working on fluorographene at the University of Manchester. He'll be able to tell you.
Yeah. At present, are there any commercial applications?
There are lots of prototypes kicking around. It's only been 10 years. We have to optimize the quality, reproducibility, and so on. There are lots of companies that have prototypes. Price is still a factor. The price needs to come down to make it competitive. But we expect within the next 2 or 3 years, they'll certainly make an impact.
And a follow-on from that, what sector? What's the business that is likely to dominate first? Oil and gas, for instance.
Composites will probably be the first one to make an impact. So applications or sectors where you need lightweight, strong materials, where they're willing to pay a slightly higher price. Those will be the ones that will, where you'll see first things like aerospace,
Right.
or defense sector where price is less of an issue. You just need the quality. So something like that is likely to be the first commercial use. You may not even hear about it if it's a aerospace application, but that's likely where it will make a difference.
Years ago, I remember doing carbon deposition in the vacuum chamber. Admittedly, it wasn't terribly well controlled. It was for surface replication. Why can't that be used as a method for making graphene?
It does. It is. That's the chemical vapor deposition I was telling you about.
You said you're using methane for that. This was just a piece of carbon being sputtered onto the surface substrate.
Yes, there is some work into. You can't just sputter it on. It doesn't give you the kind of control you need. You have to use what's known as a molecular beam. So it's called molecular beam epitaxy. There's some work going into that route, but it's jolly expensive. So it's not a commercial route yet.
Has anyone done any work at very low temperature with graphene?
Well, a lot of the electrical measurements are extremely low temperature measurements.
How low are the interesting properties that emerge?
Plenty. Electronic devices behave very, very differently at low temperature. So we can actually get what are known as single electron transistors. So you make a device with graphene where you can literally count the electrons going from one side to the other one by one. You can control it even one step further. You can actually check what is the spin of the electron going through at that temperature. And you can play with the spin of the electron. So in normal devices, electronic devices, like a bit is 1 or 0. So 1 is when there's current flowing through, 0 is when there's no current flowing through. In spintronic devices where you manipulate the spin, 1 is up and 0 is down, but then you can have in-between states. That's basically quantum computing, so that's where that's headed.
So is there a promise of maybe computing coming out of it?
Yeah.
So there's a big implication for storage, is it?
Absolutely. Yeah. Data storage, data processing. But it's you need large areas of extremely high quality graphene. At the moment, these devices, because of the quality requirement, they're made on single pieces of sellotape graphene. We don't have a large area graphene of sufficiently high quality to actually make commercial devices. So while we've demonstrated them in the lab, the technology is waiting for this large area production to catch up. It was the same thing with silicon as well. You could make silicon devices, but until people could make large wafers of silicon, the silicon microchip didn't take off. So it's a similar situation.
When you described the multiple layer technique at the end,
Yeah.
I assume that you were using chemical vapor deposition.
People are trying, but these materials don't readily grow on top of each other. So no one's really demonstrated it through that route yet. But yes, that's the ideal way. If we could do that, it would be extremely scalable. Right now, again, those kinds of devices are all done one at a time. It takes about a month to make a device. It's good for measuring the properties, demonstrating interesting devices. It's completely non-scalable until somebody licks that problem.
In the list of superlatives you have, there was one that said it's very transparent to light.
Yeah.
And then the one afterwards said a single layer absorbed.
Yeah, so okay, I glossed over that a little bit, but on one hand it's 97% transparent, but a single layer absorbing 3% is great. So it depends on if you want to use it for a photo detector or if you want to use it for a transparent conductor. Either way, it's good. That's what I was trying to say there.
You talk about its properties blocking helium.
Mm-hmm.
How porous is it to hydrogen?
Helium is smaller.
Oh, sorry.
It's completely impermeable to everything. When you say something, so the helium leak tight is the gold standard. So that's why I said helium.
Despite the defects in the
That's why you have multiple layers on top of each other, not a single layer. Then you'll have defects through which individual atoms can get through. But when you have few layers on top of each other in like a filter paper structure, then it's completely impermeable. Yes?
Are there any interesting properties observed interacting with RF? Where they kind of build these waveguides and things like that?
Yes, so you can make RFID tags with printed graphene, RF antennas. So it's a conductor. You can you have RFID tags made with copper. You can do the same with graphene. Okay.
Is that wrong? Okay. Well, I hope you enjoyed it as much as I did. Thank you all for coming tonight. Hope you all thank Dr. Aravind.
Thank you.